So now we want to talk about the expression of equilibrium constant for reactions that are related to each other. And what do I mean by related? I mean that this reaction can be related to some other reaction that already exists and have a known K by some kind of manipulation. And this is something that you might recall we studied in the topic of Hess's law in Chem 11. So I'm going to list some of the relationship that you might observe from one reaction to another reaction. So one is when you just reverse the reaction. Okay, so a lot of times you might write the reaction A goes to B, and then it has a certain K value. Well, what about the K value for the reaction B goes to A? Well, as you might imagine, if this one is B concentration at equilibrium over A concentration of equilibrium, this one is just the reverse. So therefore, if we call this one K of the old reaction, then the K of the new reaction is just 1 over the K of the old reaction. Hopefully that's pretty obvious. So if we have K2 for the new reaction, then we would just say that that's equal to 1 over K1. Now here's another one that we commonly do to a reaction, which is multiply them. So we might start with the same reaction A goes to B, but then we say now, okay, what about if we are interested in the reaction 2A goes to 2B? What is the K of that reaction? Well, this K new will just be B squared over A squared, but that's the same as B over A both squared, of course, which means that that itself is the old K expression squared. Okay, so in other words, if you multiply a reaction with a number, and let's say that number is n, then your new K is just the old K raised to the power of n. Okay, so you see that in the notes there. All right, now let's talk about the third type of manipulation that we often see, which is when you add reactions together. So this often happens as well in equilibrium situation. Let's say you have A goes to B and you have another reaction C goes to D, and you add the two reactions together. The resulting reaction is something you're interested in. So this becomes A plus C goes to B plus D. Okay. Now you might imagine if this is K1 and that's K2, what is the new K here? K3, let's say, or K new. Well, here the new K would just be B times D over A times C. But B over A, this one is K1. And then B over C, that's K2. So it's just the same as K1 times K2. So you can apply this to any time you add reactions together. The new K is just the product, multiplication of all the existing K. Let's put this idea into practice. We have a reaction that's given here. 2NH3 goes to N2 and 3H2. It has a K value of that. And then they say, what is the K for this related reaction? Has the same three species, looks slightly different, but let's figure out what happens there. Okay, so this is our main reaction. Now we have this new reaction. If you see what happens to the new reaction compared to the old reaction is that first, the products have become reactant, the reactants have become products. So we've reversed the reaction. That's one step that we did. Then we see also that everything has been multiplied by 1/3, because then we have H2 with coefficient of 1, N2 with coefficient of 1/3, and NH3 with coefficient of 2/3. So two things have happened. We reverse it and we multiply it by 1/3. So what happens when we reverse something? It becomes 1 over. We do the reciprocal of the old K. Okay, and then what happens when we multiply something by a number? We raise that to the power of the number, which is 1/3. If we put these two changes together, then our new K should just be the reciprocal of our old K raised to the power of 1/3, which is the same as taking the cube root of that number. Now, if you plug in the old K in that expression, you should get a final answer of 42.5. So we had said earlier that the magnitude of the equilibrium constant tells us how favorable the reaction is, whether it's towards the reactant or towards the product. So as a reminder, if the K is really large, much larger than 1, then we would say that it's product favored, or it lies to the right. And then when it's much smaller than 1, but again greater than 0, because K cannot be negative, it would lie to the left, or it would be reactant favored. Okay, here are just some examples of these values, just to give you a little bit of a feel for how wide the range of K values could be. Okay, so you have reactions where the K is 10 to the 83rd. You can see that that pretty much is an irreversible reaction, right? If you have a K value being that large, pretty much that means that at equilibrium, all you'll see is just product. okay, because the reactant concentration is going to be so low. You also have reactions where the K is really tiny, 10 to the minus 23rd. You see some smaller one later on in the semester, but that just means that there's not a whole lot of progress that's been made in the reaction at equilibrium, right? By the time you reach equilibrium, most of your reactant's still there. You have very little product, whereas in this one, it's the opposite, very little reactant in that first one. Okay, and you have reactions where they're kind of close to one, so in which case you have about the same of both reactants and products. Okay, and not only that, here's the thing that's interesting. These K values actually depends on temperature, so you can see that a reaction is really unfavorable. Okay, we'll use this word again and again later on. Unfavorable just means that it doesn't favor product, right? So 10 to the minus 21, a really tiny number at 298 Kelvin, which is about room temperature. But then if you crank up the temperature to 1100 Kelvin, now that reaction actually has pretty favorable K. It says a K of 10. So you can actually change the value of K with temperature. Now you might think back to kinetics and remember that the rate constant is also changeable by temperature. So both of the constants are actually affected by the temperature that the reaction is done at. And we would go back to this idea later on. We talk about Le Chatelier principle and how to manipulate reactions to make it more favorable or less favorable. Now, the value of K not only tells us how favorable the reaction is, whether it's reactant side or product side, but it also allows us to predict which way the reaction is going to go. So in other words, we can use it to predict the direction of a reversible reaction. Now, why do you think that's important? Well, because reversible reactions can go both ways, right? It could go to the left, it could go to the right. So at any point in time, we should be asking ourselves, is my reaction going to make product or is it going to make reactant? As a net, I'm talking about over time, would it continue making reactant or would it continue making product? That is an important question, because if we're trying to make product, but then the reaction is actually going towards making reactant, then we're just wasting our time waiting for it to progress. So how can we determine the direction of a reaction? One way that's really easy is just to see what's present initially. So let's think about that. Let's say you have a reaction here, which is the nitrogen-hydrogen reaction to form ammonia, and you have the equilibrium constant given right here, 6.02 times 10 to the minus 2. The key point to keep in mind about this number is just that it's not zero. You have to have some product over some reactant, right? So there has to be some kind of product here at the end relative to the amount of reactant. Okay, so if you start your reaction like this, which is showing that you have reactant present but you have zero product, what do you expect to see? You expect the reaction to go forward towards product. Why? Because at equilibrium, we expect to have some ratio of product to reactant. Again, the number is not zero. So in this case, if we start with this initial condition, again, notice I'm using the word initial and then I'm using the word equilibrium, right? So initial means the starting point, equilibrium means the ending point, right? So if I'm starting with this, then I can easily predict that the reaction will go forward, will go towards product, okay? Because you don't have any product to begin. What happens when you start with the second initial condition? Here you have no reactant. You only have product. What do you expect to happen? Same point. Products over reactant is supposed to equal to 6.02 times 10 to the minus 2. So there has to be some number for the top. There has to be some number for the bottom, just mathematically. So therefore, not having anything for reactant doesn't make sense. So the only possible explanation, then, the reaction must be going the reverse direction in this case if you start with these initial conditions, right? And the reason is because there's no reactant there. Third situation is hard. You start with some quantities of both. How do you know which way it's going to go? And that, of course, kind of the situation that we really need to think about a little bit. We have both of them. Are we going towards the product side? Are we going to the reactant side? There's actually a way to tell by looking at the value of this equilibrium constant. Okay, so remember that our K is 6.02 times 10 to the minus 2, okay? So we know that when we're done with our reaction, right? Because remember, equilibrium means that you're done with your reaction. The ratio of NH3 squared over N2 times H2 cubed should be equal to this number right here. So how does that help us? Well, we know that we start with these numbers here for our concentration, 2, 1, and 3. So if we we calculate the ratio of these three species using exactly the same expression as the equilibrium constant. Compare it to that equilibrium constant number, right? The 6.02. If that number is not the same, then we know we're not at equilibrium. That's the first point, right? The second point, if the number is less than k, so think about that, right? So we calculate the number. If the number is less than k, that means we still need to make more product, right? Because in order for us to reach k, the number has to get bigger. The only way to get bigger is if you increase the numerator and decrease the denominator, which means you're making more product, consuming reactant. If that number we calculate is bigger than k, that means we have too much product, we have too little reactant, so we have to go in the reverse direction. Hopefully, conceptually, that makes sense. That number that we're going to calculate, that is exactly the same expression as the equilibrium constant expression, is called the reaction quotient, or Q. Okay, so we differentiate it from K because it's a number we calculate using exactly the same expression, but we just use initial concentration or non-equilibrium concentration. So I really want to highlight that idea that Q is calculated using non-equilibrium concentration. K is calculated using equilibrium concentration. And we compare Q versus K to find direction of reaction. So let's do that. We just said that we don't really know which way this is going to go, so I'm going to calculate my Q, okay? So my Q is going to be using the same expression, right, which is ammonia squared. So what's my ammonia here? That's 3, so it's 3 squared over our N2 concentration times our H2's cube. So our N2 is 2, our H2 is 1, and that 1 is cubed. So what's the answer here? Well, 3 squared is 9 divided by 2 times 1, it's 1 cube is 1, so it's just 4.5. Now, how does 4.5 compare to the K value? 6.02 times 10 to the minus 2. 4.5 is bigger than 6.02 times 10 to the minus 2. Okay, so if it's bigger, think about it, right? Your K expression is shown on the left there, which is products over reactants. This number right now is bigger. This is what you want to be, right? This is product at equilibrium, reactant at equilibrium. So this initial value, call it IN here, initial value is bigger, so you need to make it smaller, so less product, need more reactant to get to the K numbers. So if I need less product and more reactant, what does that mean? That's going in the reverse direction, okay? Reverse direction. So that's how you tell. So you're gonna need to calculate Q, and let me just summarize the information right here. So if Q is less than K, then the reaction will go from left to right. So sometimes we would use this word called going right shift. We use this in two different settings, but this is one of the settings we're going to use that word, shifts to the right. Okay, it's going to move to the right. We'll use it later also for Le Chatelier. If Q is greater than K, that's the situation we just encountered, the reaction will then go from right to left, which is going to consume products, make reactants. That's what we just said with our specific situation, right? And then lastly, Q is equal to K. What happens is already equal to K. Well, that means the reaction is already at equilibrium. So it's not going to go anywhere. It's just going to stay there because it's already done, okay? I want you to think a little bit about this problem here. Since we already did that other problem as an example, you should be able to do this example right here. Think through that a little bit and see which direction this reaction will go, okay?